In this lecture, we are going to work on a notebook to just do text preprocessing so we can explore a little bit how it works. This lecture will be useful before we move on to the next script, where we will assume that we already know how it works. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Okay, so we're going to start by making some fake data. Since we eventually want this to be saved as a CSV, it's convenient to create a data frame. But in order to do that, a convenient way to specify the data is in a dictionary. So in this dictionary, the keys refer to our eventual columns, and the values are lists that correspond to each row in the data. So we're going to have 3 samples in our data set. The labels are 0, 1, and 1. The sentences are, I like eggs and ham, eggs I like, and ham and eggs or just ham. I've added some punctuation to this data set so we can see what happens to it in our tokenizer. Next, we pass this data into the data frame constructor to instantiate a data frame. Next, we do a df.head so we can look at the data frame. Hopefully, this is what you expected to see. Next, we save the data frame to a CSV file by calling the toCSV function. We can also use the command line version of head to see the contents of the file. Next, we're going to create our 2 field objects, one for the text and one for the label. For the text, I've set sequential equal to true since our data is a sequence of words. I've set batch first equal to true since I want the data to be n by something rather than something else. I've set lower equal to true so that the data is lowercased. I've set tokenize equal to spacey. This might seem odd to you, but spacey is another NLP library in Python that is somewhat tangentially related to PyTorch. Basically, if you leave this argument unset, it's just going to use string.split by default. I would recommend you try both to see what the differences are. I wanted to use spacey here to show you how it deals with punctuation. Finally, we set pad first equal to true so that the padding goes at the beginning of each sentence rather than at the end. Next, we set the label field. Here we set sequential equal to false since this column does not contain sequential data. We set use vocab equal to false since this column contains no vocabulary and it's just integers. And finally, we set is target equal to true since this is the target column. Next, we create a tabular dataset object where we pass in the CSV file we created earlier. We set format equal to CSV since it's a CSV, and we set skip header equal to true since Pandas saves the header row by default. We set the fields argument to a list containing the fields we just created. One important note is that these fields must be specified in the same order as they appear in your file. So if your file contains the data column to the left of the label column, you would put the data field first. So if you check the attributes of the dataset object, you'll see it has one called examples, which is a list of example objects. What I've done here is I've grabbed the first one so we can see what's in it. As you can see, there's an attribute called data. And if we look at this attribute, we can see that it contains our sentences, but not in their regular form. In fact, our sentence is now tokenized. You can see that the period has been separated from the word ham, which would not be the case if you just did a plain string.split. If we look at the label, it just returns 0, as we would expect. Next, I'm going to split the dataset. This is kind of weird in our case since the data only contains 3 samples, but let's just pretend this is okay. Next, we're going to call the build vocab function on our text field and pass in the train dataset. Oddly, this is not done automatically when you create the dataset object. Again, it's not a mature library. Next, we call the vocab attribute and check its type. We can see that it is a vocab object. Next, we call the attribute s2i, which returns a dictionary. Since our dataset is so small, which I did on purpose, we can see the entire dictionary. As you can see, each token in the dataset is assigned a unique integer. Also, punctuation is considered a token, since we use the spacey tokenizer. We can see that the unknown token gets assigned the index 0, and the pad token gets assigned the index 1. We can also see that all the words are lowercase. Next, let's look at the I2S attribute. We can see that it contains a list of our tokens. You should confirm to yourself that the indices of each element in this list corresponds to the values in the dictionary above. Next, we create our device object, as we normally do. Next, we create an iterator from our datasets. We set the batch size equal to 2, since both the train and test set only have a maximum size of 2. Next, we loop through the train iterator and print the inputs and targets along with their shape. As you can see, the shape of the inputs is 2 by 7. Next, we do the same thing for the test iterator, and the shape of the inputs is 1 by 6. So what do we learn from this? Well, we learn that PyTorch already intelligently makes your batch size have the smallest sequence length possible. There is no unnecessary padding in the train batch or the test batch. This is good since, for example, if our data has a maximum sequence length of 10, but the sentences in our batch only have length 2 or 3, then that would be a huge waste of computation. Finally, if we look at these sequences of integers carefully, we can probably deduce which sequence belongs to which original sentence. The one with all the padding is the easiest because that corresponds to the shortest sentence in our small dataset. As an exercise, here's what you want to do. Instead of just deducing which sentence goes with which sequence, make use of the index to token mapping from earlier to programmatically convert these sequences back into their original sentence form.